So, first of all, let's fundamentally look at work and heat. So, we can say that work can always be converted to heat directly and completely. So, for example, if we have a rotating shaft here in water, then if we rotate this, then this little propeller essentially will generate heat, will generate friction. And there'll be an output of heat to the water. However, if we have that shaft sitting stationary, not moving, and we heated the water up, then we would not see the shaft starting to move. We know that from our experience. So the reverse is not true. We cannot take heat and convert it easily to work. Then what is the purpose of a heat engine? Well, that is the purpose of a heat engine, to take heat and try to turn it into useful work. And that's what we do in our car engines and aircraft engines and steam power plant. So the purpose of a heat engine is to take this heat and turn it into useful work. But the thing is, we can't turn all of the heat into useful work. Unfortunately, it's just not possible to do that. We can't complete the engine cycle if we try to do that. So what we have to do is reject some of the heat to a sink. So we turn as much of the heat into work as we possibly can, and the rest is rejected to a low temperature sink. So for example, it's rejected into the atmosphere or it's rejected into the ocean. So on the left here, you can see a diagram that kind of explains what a heat engine does. So this circle in here is representing the heat engine itself, and then there is a transfer of heat into the heat engine from a high temperature source. So that high temperature source can be a furnace or even a nuclear reactor. So the heat engine will take as much of that heat as it can and turn it into useful work. So that is our network output. And that can then be used, for example, to generate electricity or to keep a car moving. The rest of the heat is then rejected, it's disregarded, it's rejected to a low temperature sink. So that sink can be, as I said, the atmosphere or a river or the ocean. So all of this operates on a cycle. It's a constant repetition of four processes essentially that's repeating on a cycle. So we can categorise these heat engines as either internal combustion or external combustion. And that depends on basically how the heat is supplied to the working fluid. So in an external combustion engine, such as the steam power plant that we just looked at, the energy, the heating, is supplied to the fluid from an external source. So that's like a furnace or a nuclear reactor. In an internal combustion engine, like what you have in your car, then the heat transfer and the energy in is supplied actually to the working fluid by burning the fuel inside the system boundary. So that is an internal combustion engine, whereas a steam power plant is an external combustion engine. It is worth noting here that the thermodynamic side of things is pretty much the same regardless of the fuel that's been used. So whether it's a fossil-based fuel like coal or oil, or whether it's a nuclear fuel, the thermodynamic cycle is pretty much the same. It's just the actual heat source that's different. So in a conventional power plant, we're basically using the molecular energy of the coal or the oil. and that is used to generate our heat. But in a nuclear power plant, we are using usually nuclear fission, to release energy from the atom and use that as heat, so that that is then converted into work. But the thermodynamic cycle for both is very similar. It's pretty much the same. It's worth noting here that the overall thermal efficiency of a cycle is essentially a combination of two things. It's a combination of the source efficiency, so how much energy can actually be taken from that source. So that will vary depending on whether it's oil or coal or nuclear energy. But then the second part of that efficiency is what we call the cycle efficiency. And that's what we're more interested in, how we can actually make these power cycles, these work generating cycles, more energy efficient. If we focus on the cycle efficiency, then we can think about, okay, what's our desired output here? Well, our desired output is to get as much useful work out as we possibly can. So as I said, the net work output is really what we're interested in. So that is equal to the work output minus the work that has to sort of go back into the system to keep it running. So that could be, for example, due to a pump or a compressor, which is taking work from the output, usually a turbine, and putting it back into the system to increase the pressure of the fluid. So the net work output is equal to the net heat transfer of a cycle, which we discussed previously when we looked at thermodynamic cycles. So what we can say is that the thermal efficiency of a heat engine will essentially be equal to the net work output, which is our desired output, divided by our required input, which is our Qin. So it's our net work divided by our heat transfer in. But we can say that the net work transfer is Q in minus Q out. So we can also express our thermodynamic efficiency of the cycle as 1 minus Q out, heat transfer out, or a rejected heat transfer divided by heat transfer in. So that is two different ways that we can calculate our thermal efficiency of the cycle. And that's what that symbol there means, thermal efficiency. So different systems will perform better than others, and we need to be able to examine the performance, and we do that by looking at the thermal efficiency